Okay everyone, this is section 1.1. We are going to be applying properties of the real numbers. So our two goals for this section are to be able to describe subsets of the real numbers and use properties of the real numbers. Okay, so this is our real number system. It has two major subsets here, what we call the rational numbers and the irrational numbers. So starting with the irrational numbers that are kind of by itself, these are the numbers that go on and forever and ever and never really stop. So these can be the square root of 2, which is really as a decimal 1.414, going on and on forever. Or we can have negative square roots, like the negative square root of 14. That's going to be negative 3.741, on and on and on. Or even pi. We really know that as 3.14, going on and on forever. So these never stop. On the other side, we have the rational numbers. So these rational numbers can be like fractions or decimals that repeat. So like 0.333, that's repeating on and on forever. Or like negative 1.1 repeating. They're just repeating or terminating those numbers. Within the rational numbers, we have what we have called the integers. Okay, the integers can be negative, like negative 7, or they could be positive, like 10, or 102. Okay, they can be as small as you want or as big as you want. But within the integers, we have what we call the whole numbers. These include 0, or 13, okay, any positive number that you can count on your fingers pretty much. We can have 1,001, too, for example. So these are the whole numbers. Okay. So for example 1, we're going to graph these real numbers on the number line. So first we have negative 7 over 3. Well, if we were to turn that into a decimal, negative 7 over 3 is really just negative 2.3 repeating. And if we turn the square root of 5 into a decimal, the square root of 5 is really just 2.236, and it goes on and on forever. Okay, so if we were to graph these real numbers on the number line, if I start with negative 7/3, well, that's a negative number. So I'm going to go left on my number line. It's going to be in between negative 2 and negative 3, but it's only going to be not quite in the middle. So just to the left a little bit from negative 2 is negative 7/3. And if I want to graph the square root of 5, well, that's positive 2 point and a little more. So a little bit bigger than 2, we have the square root of 5. So there's our numbers on the number line. In example 2, I have here a table of elevations from 6 different continents. And it wants us to put the elevations in order from highest to lowest. So, well, if I look across here, they're all negative. So if I'm at the highest number, I'm thinking about the number that's closest to 0 first. And if I scan through here, the number that is closest to 0, or the highest, is Australia right now. That's negative 16. And then my next highest would be Europe with negative 28. And then South America with negative 40. And then North America with negative 86. Africa with negative 156. And finally, the least or the lowest elevation, which was what we wanted, was negative 408. So here we have highest to lowest elevations. All right. So next up, we have all of our properties for our real numbers. Okay, so A, B, and C here are just normal numbers that you would see normally. Okay, so our first property up here is what we call closure. Closure is just if we have two numbers, like A and B here under the addition column, if you add them together, it's just going to be another number. Or if you multiply them together, it's going to be another real number. Okay. Next up on the commutative property, it says under addition, well, I can add any two numbers and I can flip-flop them and add them. Well, it's still going to end up with the same result. Same thing with multiplication. If I add two numbers and then flip-flop them or reverse them the other way, I'm still going to get the same answer. The associative property says, well, let me add or multiply these two numbers first and then add or multiply it by another number. Well, it's going to be the same thing if I pick the other two numbers, add or multiply them, and then add that other number that I started with before. Okay, so if I have A and B and then I add C, well, it's really going to be the same thing as if I add B and C first and then add A. Or if I multiply A and B first and then multiply by C, well, let me switch it around and do B times C first and then multiply by A. The identity property is basically if I have a number and if I add it to 0, I'm still going to get that same number I originated with. Or in the multiplication way, if I multiply by 1 by a number, I'm still going to get that original number. Any way you do it. It kind of goes in hand with the inverse. It tells me, well, if I have a number and I add its inverse, I'm going to get back to that identity. Okay, that's the goal with the inverse. Same thing over here with the multiplication side of it. If I multiply by the inverse, I'm getting back to that identity, which in this case, under multiplication, that's 1. So our goal is to get back to the identity when we multiply by an inverse. And our last one here, the distributive property. Okay, we've kind of seen this before. If I take a number, I am going to distribute it to both things in my parentheses. Same thing if I multiply. Okay, it's just going to be pooling whatever we have in common out. In this case, that's the A, which is what we originated with. Okay, so in example 3, it wants us to identify the properties that the statement illustrates. So in the first one, 6 plus 3 plus 1 is equal to, well, if I add 3 plus 1 first and then add 6. Well, if I go back up to my properties, well, that's the same thing as my associative property. Right? Because I had parentheses, I'm adding two numbers first and then adding another one, which is the same thing as adding the other two and then adding the one before. So this one right here is our associative property. And the next one, in B, it tells me, well, I'm going to take 2 times 5, but it's the same thing as doing 5 times 2. So I'm flip-flopping them around. And we've seen that up here in the commutative property. Well, if I have A times B, or a number times a different number, I can just flip-flop them around and I'll still get the same answer. So B is our commutative property. So that's our example 3. A couple of vocab here. We have an opposite. Okay. The opposite is the number negative b for any number b, and we also call that the additive inverse. The additive inverse. So if we have, for example, say 7 minus 5, that's the same thing as 7 plus negative 5. We're just having that additive inverse in there. So we know 7 minus 5, that's really 2, but 7 plus negative 5, that's still 2. So our additive inverse. A reciprocal is the number 1 over b, so it's going to be a fraction for any non-zero number b, also known as the multiplicative inverse. So, for example, if I have two numbers a and b, let's say 4 divided by 2, for example, and I want to do the same thing on the other side. Well, that number a is still 4, but I need to make 2 as a fraction. So multiply 1 over 2. That's my multiplicative inverse. But I need to make sure b isn't 0. Because if you remember, any number over 0 is undefined. Okay, so 4 divided by 2, we all know that's 2. And 4 times 1/2 is still 2. Okay, so basically with the reciprocal, we know that the opposite of multiplication is division. So our multiplicative inverse has a fraction, which indicates division. Whereas if we look at our opposite, the opposite of addition is subtraction. So we have our additive inverse, or that negative b, or negative number. So with example 4, here we're going to be using the properties and definitions of the operations to show that this expression equals 3. So first what I'm going to do is just go ahead and rewrite this. So 2a plus 1/2 times the quantity 6 minus 4a equals 3. And again, that was given to me. So first what I want to do is take my 1/2 and distribute that 1/2 to everything inside the parentheses. So 2a and then 1/2 times 6 when I distribute is just 3. And 1/2 times negative 4a is negative 2a. And again, that still equals 3. But we use the distributive property. Then what I want to do here is kind of rearrange stuff. And if you remember back up in our properties, to rearrange or kind of flip-flop, we put them beside each other. We call that the commutative property. So if I go through here, 2a plus negative 2a, or 2 plus negative 2, well, that's just 0. Then I got left over plus 3 equals 3. Well, what we did here, that 2a plus a negative 2a, and we got back 0. That was our additive inverse, because we got back 0. And then 0 plus 3, that is 3, which still equals 3, and that's just the identity, saying that something equal itself is the identity. With example 5, we're going to be actually working with some units. So we're going to be working with part A first. So if you travel 3.4 hours at 65 miles per hour, well, how far did you go? So let's see, I went 3.4 hours, and I traveled at 65 miles per hour. So as a fraction, 3.4 hours. And I'm putting that over 1, and 1's just a normal unit. And I'm going to need to multiply that by 65 miles in 1 hour. And if you notice here, the reason why I'm putting an hour on the bottom is because I want to cancel the hour units out. So these are going to cancel out. So what I'm going to do here is take 3.4 and multiply that by 65. So 3.4 times 65 miles per hour is just 221 miles. So you went 221 miles in that amount of time. And with B, well, we're going to need to do 35 miles per hour. And we want to know, well, what's that going to be, or what's their speed going to be in feet per second. So with this one, I started out with 35 miles, and I did that in 1 hour. Well, we want seconds. So first, let's try to cancel out our hours and make it into seconds. Well, we all know that, okay, in 1 hour, and again, I'm putting up top so these can cancel, in 1 hour, there's 60 minutes. But I'm still not there yet, right? Because I need seconds. So again, I'm going to need 1 minute up top, so my minutes can cancel. And I know in 1 minute, well, there's 60 seconds. And that works out because I need seconds. So I had the seconds part, but I still need feet. And I'm in miles. So, in 1 mile, there's 5,280 feet. And I'm right now because I got feet, I got seconds, and they asked for feet per second, so I'm good. So what I'm going to do, again, when we multiply fractions, you multiply all the numerators together and all the denominators together. Okay, so with my numerator, I need 35 times 1 times 1 times 5,280. So that's 184,800 up top. Then in my denominator, I need 1 times 60 times 60 times 1. And that will give us 3,600. So let's reduce that down. So 184,800 divided by 3,600. That's 51.3 repeating. Okay. And that is in feet per second. Or feet / second. So here is our answer. Okay. And in part C here, we have that you work 3 hours and earn $26. What's going to be your earning rate? So you made $26 in 3 hours. We don't want it in seconds or anything like that. We want to know, well, how much do you make in 1 hour? So if I take 26 and divide that by 3, that's just $12 in an hour. That's your earning rate. And last example here, we have example 6. We have that the distance from McConnelsville to Cleveland is about 165 miles, and the distance from Cleveland to Cincinnati is about 402 kilometers. And one big important piece of information we have is that 1 mile is approximately 1.6 kilometers. So in part A, well, we need to convert the distance from McConnelsville to Cleveland to kilometers. So that's very important, kilometers. So we know that the McConnellsville to Cleveland is 165 miles. So I know that there is 165 miles. And that's just over 1, but like what we did before in the last example, well, I need to cancel out miles. So we know that from our information up here, 1 mile is 1.6 kilometers. So again, we multiply fractions, numerator times numerator, denominator times the denominator. 165 times 1.6 in the numerator gives you 264 kilometers. So there's our answer for part A. We wanted it in kilometers. Our answer's in kilometers. Part B wants to know, well, convert the distance from Cleveland to Cincinnati. So Cleveland to Cincinnati, we want it in miles. But we're given kilometers. So they gave us 402 kilometers. And we're trying to get to miles. Oops. Okay. So again, we need to cross out or eliminate kilometers. Well, from our given information, there's 1.6 kilometers in 1 mile. Okay. So, same thing again. Numerator times numerator, denominator times denominator. So I have 402 up top divided by 1.6 in the bottom. And if you were to do that in your calculator, that's 251.25, and I can round that down to be approximately 251 miles. Making sure that's what we wanted. We did want it in miles. My answer is in miles, and we have solved it.